In this problem, we're going to talk about understanding the rate of growth of an amount of money invested at an interest rate R. So the problem comes from the book at the end of section 2.3. Suppose that a sum S naught is invested at an annual rate of return R compounded continuously. Part A, find the time T required for the original sum to double in value as a function of R. Part B, determine T, the doubling time, if R equals 7%. And Part C, find the return rate that must be achieved if the initial investment is to double in 8 years. Now, the first thing, again, that we have to do is define our function. You always want to set up your notation. Here, y of t will be the amount of money. You can call it anything you want. I'm calling it y of t, the amount of money. We don't need units. It could be in dollars. It could be in euros. It could be in yen. It doesn't matter. At time t in years. Now, the goal will be to understand how to find an explicit formula for this function y of t. What we're given here is that we start with S naught, is that y of 0 equals S naught. This is what we're given. We start by setting up, after that we start by setting up the differential equation which y of t must satisfy. Here that differential equation is dy dt equals r times y. This says the rate of growth in the amount of money dy dt is just this interest rate times y. That's the amount of extra money we get. R, the rate of growth, the interest rate times the amount of money we have. That's a basic exponential growth equation, which you've probably seen solved many times. We've talked about it earlier this quarter, and you probably even saw it in Calc 2. We know immediately that the solution to this differential equation with the initial condition y of 0 equals S naught is just y of t is S naught e to the RT. As always, you should just be very careful and check that this function satisfies both the differential equation and the initial condition. And of course, we didn't go through this here. How would you have solved that differential equation? This is a linear first-order differential equation, so you could use an integrating factor. This is also a separable differential equation, so you could apply the methods that we learned just recently for solving separable differential equations. Whatever method you use, you should end up with this function, y of t is S naught e to the RT. To find the doubling time t, we just solve the equation 2S naught equals S naught times e to the RT. This is twice the money we started with. And the question is, at what time capital T is the amount of money we have twice what we started with? So we solve for capital T. And we can do that easily. We cancel S naught and we get 2 equals e to the RT. We take logs of both sides. Natural log of 2 is RT. And then we solve for T. T is log 2 over R. And since we derived this formula, T is log 2 over R, when R equals 7%, that's written as 0.07 when you're talking about a rate of growth, we get the doubling time is natural log of 2 divided by 0.07. Remember, the natural log of 2, just you can check this on your calculator, is approximately 0.693. So log 2 divided by 0.07 is 9.902. So at 7% interest, it will take approximately 9.9 or almost 10 years for your money to double. This is actually a rule I learned when I was a small child, about 8 years old, or maybe even a little less, when my grandfather was telling me how you can compute things like doubling times when you have money in the bank and getting a certain interest rate. Back then, this was actually the early 70s. A standard savings account could get 6%, and in some years even 7, 8, or 9%. Interest rates were much, much higher then than they are now. Today, you put your money in a bank account, the interest it gets, you'll be lucky to get 1%. Typically, in a standard savings account, you'll get well under 1% interest, and you can see the doubling times will be much, much longer. So the rule of thumb I learned as a small child was you just take 70 and divide by the interest rate, expressed as a percentage. So that rule of thumb would say take 70 and divide by 7%, you get 10. Why does that work? Because log 2 is approximately 0.7. And so if you take 0.7 and divide by 0.07, you take the rate here, not expressed as a percentage, but just as a decimal number, 0.07 for 7%. 0.7 divided by 0.07 is 10. So if the interest rate happened to be 6%, the doubling time, just by this rule of thumb, would be approximately 70 divided by 6, which is like 11 2/3. If you want a more exact answer, you can just take log 2 and divide by 0.06. You'll see it's very close. Log 2 is a very important number and a very good number to remember. It's about 0.69, or even for a rough estimate, 0.7 will usually do. It's one of these numbers you should know. Now, part C of the question said if the doubling time should be 8 years, so you want to have your money double in 8 years, what interest rate do you need? Solve for R. So we just write down the equation 8 equals log 2 over R. We solve for R. R is log 2 over 8. And we compute that to be 0.0866. Or in other words, the interest rate should be 8.66% if you're going to have a doubling time of 8 years.